a little bit about me. I'm the founder of Project Cyber, and I'll talk a little bit about that later on. I also participated in Girls Go Cyber Start and came in at the top 3. This is now Cyber Start America. If you were here earlier, you might have heard the talk about that. And I also started an infosec and a chess club in my middle school. I was also invited to represent the Girls Security Organization in a NATO event. And how I got started and some tips I have. So I think it's really important and fun to just experiment and try new things. So I recommend joining courses on platforms such as Coursera and Udemy to just learn about the fundamentals of cybersecurity and also try to meet like-minded peers. And I think this is something that I can't really stress enough. I think experimentation and just trying to explore your passion is just something that will help you just have fun and learn more about things you're curious to learn about. And it's actually how I learned about quantum cryptography. Over the summer, I just did research on it and just tried to compile things from Google searching, looking at articles, and that's how I learned about the intersection between physics and cybersecurity, which is something I was really passionate about. And another tip is to join CTFs, which are Capture the Flags, which are going to help you learn just like the basics behind cybersecurity and help you get started. And I think Cyber Start America and Pico CDF are great ones to start. I also recommend reading books such as The Code Book by Simon Singh, and also just remember to have fun. So let's get started. And something I also wanted to share with you guys is how you can get involved with Project Cyber. So Project Cyber, we are an opportunity for teens to engage in conversations about digital security. And our mission is to serve as a global community for teens interested in cybersecurity. And our website, our YouTube channel, and our Instagram are all linked on here. And we are going to be creating articles on digital security, creating fun games, and a whole lot more. So please do check us out. And if you're interested in joining the team, which I really hope you are, and if you're a teen, please fill out the Google form linked here and join our Google Classroom. And if you're a cybersecurity professional, we're looking for those in college and beyond to be featured in the magazine and or be advisors. So please email at rksmissionpossible@gmail.com. Okay, moving on to quantum cryptography. So first, I think a question we might have is, what is quantum? And quantum is actually Latin for amount, and it refers to the idea of the smallest discrete unit of any physical property, and examples are energy or matter. And hence, quantum mechanics is a branch of science that deals with the world on a very tiny or microscopic scale. And one application of quantum mechanics is quantum computing. So I just had 2 images on here to show what a quantum computer looks like. So at the bottom, it's an example of a quantum computer of Google, and on the right is an IBM cryostat, which is something that we use to cool the IBM quantum computer. And a quick primer to qubits. Now, qubits is an abbreviation for quantum bits. And in computing today, or classical computing, we use bits so they can be 0 or 1. However, in quantum computing, we use qubits, which are 0 or 1. And what is really, really key, or 0 and 1 simultaneously. And this is a very key property of quantum computing. So I think a great way to like wrap your head around it is using a song. So a while ago, a few years ago, a song that was really popular was Pen, Pineapple, Apple Pen. And some of you may know it. And basically, I think we can use that song to just kind of wrap our head around how qubits work. So say I have an apple and say I have a pen. So apple would be a 0 and a pen a 1. And an apple pen together would be 0, 1, which would be a qubit. So hopefully that explained qubits a bit more. And this property of qubits of being 0 and 1 simultaneously is what allows quantum computing to be so much faster than classical computing. And the reason is the number of possible states qubits can be in grows exponentially, which allows a quantum computer to consider a whole lot of combinations at once, which a classical computer just can't do. And this makes problem solving that much quicker. Our cryptography today relies on the fact that factoring large numbers is really, really hard. So when we have quantum computers, which can break this cryptography because it can factor large numbers really, really quickly, what do? Are we in danger? Like, oh no. Actually, fortunately, for every action, there is an equal and opposite reaction. And so quantum computers are going to give rise to quantum cryptography. And there's actually like 3 types of quantum cryptography. There's post quantum cryptography, or PQC, and in detail, I'll just cover lattice cryptography. And we also have QKD, which is quantum key distribution, and there's also classical hybrid cryptography. So lattice cryptography, what are lattices? So lattices are a geometric grid of points that extend infinitely in all directions. And how this works is the data is hidden in lattices, which makes for some very difficult math problems. And the challenge is to find 2 lattice points that are comparatively close together. And this might seem simple, like on a surface level, but actually experts are relying on the difficulty of solving these problems because this actually takes even quantum computers an incredible amount of time to unravel. So effectively, our data is hidden in a way that it will make for some. Okay, so when hackers try to hack lattice cryptography, it's not going to work out because it's just such a hard problem that quantum computers are going to take so long to do. And QKD is quantum key distribution, which is a subset of quantum cryptography, and it explains how a key is generated. And one of the QKD schemes is the BB84 Protocol, which is one of the more established ways to create keys with quantum computers. So in a nutshell, this is how BB84 protocol works. There are 2 parties. There is the sender and the receiver. And step 1, the sender polarizes photons in 4 directions and then sends them to the receiver. Then step 2 is these photons are read using 2 detectors, which means that each photon is going to be translated as a 0 or a 1. The receiver then ends up with these series of 0s and 1s, but we have to remember that about half of them have been read incorrectly, and this is because the kind of detector that is used matters, and the receiver can only guess which one to use. So based on the laws of probability, 50% are going to be right, 50% are going to be not right. And then step 3 is the receiver and sender will now discuss, And the receiver tells the sender what filter he used for each photon. And then the sender is going to tell the receiver if it was right or wrong. And all the photons that the receiver got wrong are then discarded. And step 4, the photons that we're left with are now going to become our key. And we'll use this key in encrypting and decrypting our messages. Classical hybrid cryptography is another type of quantum cryptography. And basically, it uses what we have today and what we can use once quantum computers arrive and basically combines the two. And so traditional algorithms like the RSA and ECC can be used alongside new PQC algorithms. So for instance, a quantum resistant algorithm, such as New Hope or Cyc, might be used together with a classic algorithm like DHE or ECDH to generate a unique key. And to sum it up, old plus new equals voila. If you're interested in learning more and you want to explore what quantum cryptography looks like, here are some resources that I think you'll find really helpful. And looking ahead, so research is increasing in this field and the rate of progress is rising rapidly. And the word cybersecurity might just take on a whole new meaning. It won't be long until quantum cryptography develops as a field as rich as today's security ecosystems. And one thing's for sure, knowing the science behind quantum computing is going to be crucial because the future is quantum. Thank you. I think we can now take questions, so I'll just stop screen sharing.
Thanks, Rajvi. Okay, so we've got a couple of questions here for you. You mentioned earlier on at the start of your thing that you talked about ERA and Udemy. What other types of courses might people might find useful?
To learn quantum cryptography, I think the resources that I linked, I think first check out those, and then after that, something that I just found useful when I was doing some research on it was just looking up videos and articles on TEDx, and also I think if you also look up our courses on Stanford Online and things like that, you will find a lot of quantum cryptography introductions and quantum computing as well. I think if you just Google search and then also like type in like for beginners, I think you'll find a lot of resources that way.
Wonderful. Thank you very much. And then we talked a little bit about Project Cyber. Do you want to go into a bit more detail about what that is and how people could potentially get involved there?
Yeah, definitely. So, okay, let me. Should I screen share the Project Cyber? Does everyone have the links? Okay, so we are an organization or a platform for teams to basically create their own content on cybersecurity. So you are free to explore any topic of your choice in cybersecurity and write like a draft of whatever topic you choose. And then from there, there's 3 steps. We go through peer edits, and then after that, we upload it on our website. So it's basically you write a first draft, then you have peer edits, and then you polish it up. And basically, you can create articles, you can create games. It's really open up to you, whichever medium you prefer. And basically, we are going to create content on cybersecurity. And basically, it's a way for you to interact with other teams and learn critical thinking skills and just learn communication and meet other people and have fun.
Very cool. Another question here. Previously, you mentioned about the BB84 protocol and how it can present a key to decode. Could you clarify a little bit on how that works?
Yeah, so basically the BB84 protocol is used to create a key. And a key in cryptography is basically the way you transform plain text into ciphertext. So plain text is having your message in normal readable language, and then you use a key to transform it into basically something that no one can read it. And so, for instance, Caesar cipher, if you have a message such as "I am eating an apple," and then if you have a key, then a key of maybe 2 in Caesar cipher, which shifts every letter by 2, would change it up like each letter by 2. So key is basically a way to map the input to an output, and the BB84 protocol is how the key is generated, which will help us take the plain text, and turn it into ciphertext.
And then staying on to like the quantum cryptography, or not necessarily, but the quantum computing and cryptography, is modern cryptography about to be dead? I mean, once quantum computers are all commonplace, the current standards which we have, I've heard this said so many times before that, you know, quantum computers will just destroy our current method of crypto. How do you feel about that?
Yeah, that's a great question. So quantum computers are going to be a much more powerful version of classical computers. However, that doesn't mean that classical computers are going to go away completely. So things like just scrolling on social media or chatting with your friends, those things will still require classical computers. And quantum computers are going to be for like more of a high level cryptography. So what that means is something like your daily activity, like just searching online, those things you'll do with your classical computers. So those things are more likely to stay with classical encryption methods. So online banking and things like that, those things might need to be quantum resistant, which means we might need to use quantum computers for that. However, classical computers are still going to stay on. So no, our classical cryptography is not dead. However, we will need quantum cryptography to combat quantum computers. And so I think of them as kind of working together in symbiosis.
Awesome, wonderful answer. Thank you very much. Okay, I think we have one more question we're going to ask, and I think we're going to be done for now. So going back to just Project Cyber for a moment, if someone is listened and watched all of the presentations here today, and they think, wow, I have absolutely no experience doing anything in cybersecurity related, but I'd like to get involved. Can they still get involved with Project Cyber, or do they actually need to have a little bit of experience?
No, definitely. You can totally get involved in cybersecurity if you're interested in learning more. We're open to everyone, and if you're a beginner, that's great. And if you are like, hey, I really want to explore this part in cybersecurity, I heard a presentation and I want to explore more, then all you'll need to do is just do a little bit of research, or just think, how can I condense what I learned today? And basically, you can either do more research, or you can just write based on what you know, and based on the topic, you can create like maybe a 500 word, 600 word article, and from there we will just move on to peer edit. So definitely, if you're a beginner, you're welcome to join. We hope you join.
Wonderful. Thank you very much, Rajvi. It's been a pleasure having you on to present today, and I'm going to echo the sentiments of some of the other people I've been chatting with, is that we hope we can be like you when we grow up.
Thank you so much. It was awesome being here. Thank you so much.